Everything your body does, from your eyes detecting light to your system reacting to medicine, it all comes down to a decision. And I'm not talking about a decision in your brain, I mean a microscopic choice, one that's happening billions of times a second, deep inside every one of your cells. So let's dive in and uncover the body's most fundamental switch, the one that makes it all possible. It really all boils down to this one single, incredibly elegant component. It acts like a universal on-off switch for just about countless biological processes. So the big question is, what is this thing and how in the world does it work?
Well, the answer, as it turns out, is an amino acid called cysteine. And it's kind of this unassuming hero at the very heart of how our cells talk to each other. It's unique, it's chemically clever, and boy, does it have a remarkable trick up its sleeve.
So what's the big deal with cysteine? What makes it so special? Well, it's all about this little section at the end called the thiol group. That's the SH you see there. That tiny little pair of atoms, sulfur and hydrogen, is basically the entire engine of the switch. It's what gives cysteine its incredible power to sense what's going on around it and react.
And the way this switch works is just unbelievably elegant. All it has to do to flip between two states is lose a single proton. That's it. In its neutral thiol state, it's off. But when it loses that proton, it becomes the negatively charged thiolate state. And boom, it's on. It's a tiny, simple, reversible electrical change that leads to absolutely massive consequences.
Right, so here's the crucial part. What happens after that tiny electrical flip? Well, that new negative charge, which is now buried deep inside a receptor protein, suddenly acts like a tiny magnet. It starts pushing and pulling on different parts of the protein around it, causing the entire structure to literally shift its shape, to change its conformation and turn on. It's a beautiful transition from an electrical spark to a physical, mechanical action. Okay, so let's take this into the world of pharmacology, because this idea completely changes our understanding of medicine. You know that old lock and key model we all learned? It's not the full story, not even close. This switch gives us a much more elegant way to explain how drugs actually do their job.
This right here is a huge paradigm shift. A ligand, which is really just any molecule that binds to a receptor, like a drug, it doesn't force the receptor to change. Instead, the receptor is already flickering back and forth between on and off all the time. The drug just shows up and acts like a stabilizer, basically persuading the receptor to hang out in one state a little longer than the other.
And this new model completely redefines how we think about different kinds of drugs. A full agonist, right, a drug that gives you a really strong response, is just a molecule that's amazing at holding that receptor in the charged on state. A partial agonist gives it a little nudge, a little bit of stability, so you get a weaker response. And an antagonist, a blocker drug, well, it binds, but it offers zero stability to that on state. It just gets in the way and stops a response from happening.
Now you're probably thinking, a highly reactive switch like this, buried in a chaotic cell, it must be incredibly vulnerable to damage, right? Well, you'd be right to think that. But nature has come up with this absolutely ingenious solution to protect its most important component.
I mean, it's the logical next question, isn't it? The inside of a cell is a pretty wild chemical environment. You've got all these damaging molecules called free radicals floating around. So how does this delicate, crucial switch actually survive all that chaos?
The answer is something called the ladder of sulfur states. See, if the switch gets hit by oxidative stress, it doesn't just break. No, instead, it climbs up this ladder into a temporary, reversible, protected state, something like a disulfide bond. You can think of it like a safe harbor that shields the switch from any permanent damage.
Honestly, this is the perfect analogy for it. The switch doesn't burn out when there's a chemical power surge in the cell. It just trips a reversible fuse. And once the danger, the oxidative stress, is gone, the cell's own systems just reset the fuse. And the switch is right back in business, good as new, ready to start signaling again. It's brilliant.
Okay, so we've seen the switch, how it works, and how it protects itself. But, a single switch on its own doesn't do much. The real magic, the real power, comes from how the cell reads the combined effect of billions of these switches all at once. And the answer is just so cool. It connects biology to the fundamental mathematics of how we perceive the world.
So get this, the cell doesn't sit there and count every single active receptor one by one. That would be crazy inefficient. Instead, it just senses the change in the balance, like on a beam balance, between the whole population of off receptors on one side and on receptors on the other. This whole idea is captured mathematically in what's called the net shift model. And don't worry, you don't need to be a mathematician to get the core idea here. The response isn't about the total number of things happening, it's all about how much a drug or a signal shifts the balance,
how much it tips the scales from one side to the other.
Now, for a second, let's just step completely out of the cell and into psychology. There's this fundamental principle called Weber's law that describes how we perceive the world. For instance, it's way easier to notice a single candle being lit in a pitch-black room than it is to notice it in a room that's already brightly lit, right? Our perception is all relative.
And here it is. This is the incredible connection. The math that describes how a whole population of your cells responds to a drug is the exact same math that describes how your mind perceives the world around you. That cellular beam balance works on the exact same principle as our perception of candles in a room. It's a universal law of perception, scaling all the way from a single molecule to your conscious mind. Just amazing.
So what does this all mean? What are the big implications of this one tiny little switch? Well, when you start to scale it up, it becomes something truly extraordinary. It becomes the very blueprint for the body itself.
And just look at where this switch is found. You quickly realize just how fundamental it is. I mean, this is not some obscure one-off mechanism. We're talking about the opioid receptors that manage pain, the rhodopsin that lets you see this right now, the adrenergic receptors that control your heart rate. The cysteine switch is the core engine for all of them. It is a truly universal principle in biology.
So when you get billions of these tiny electrical switches firing together across your tissues, they're not just sending simple little signals anymore. They're generating these complex, large-scale electrical fields. And what researchers have discovered is that these fields aren't just random noise. They're an instructional language. They're a blueprint. These bioelectric blueprints literally contain the information that guides how an embryo develops into a person, how a salamander can regrow an entire lost limb, and even how to suppress the growth of cancerous tumors, basically by reminding those cells of the grand plan, what they're supposed to be doing.
So, at the end of the day, the crucial takeaway is this. The link between that little cysteine switch and GPCRs, which are the largest, most important family of receptors in your entire body, it isn't just one cool mechanism among many. It is a foundational, unifying principle that connects the chemistry of a single atom to the architecture of an entire living organism. And that really leaves us with a fascinating final thought. We are just beginning to understand this incredible bioelectric language. So if we can truly become fluent in it, if we can learn to read and even write the body's own electrical blueprint, what new frontiers in medicine, in regeneration, and in healing might we be able to unlock?